And it's recording. All right, team, let's do a bit of a recap. So, by the time you're in year 11, especially at this stage, you should have learnt these graphs. Okay, so at year 7 and 8, you don't know what graphs are. You only learned patterns. And one of the first patterns you learn is mx plus c. That's a straight line equation. And you learn that in year 7 in terms of table of values, so kids actually don't realize it. They just have an x and y. They get a rule, so for example, 2x. And then they just get 0, 1, 2, 3, 4, and they say fill in the y values. That's what you did in year 7. Okay, and the whole idea of that was so that students eventually understand there is a relationship between what you put into the equation and what you get out of it. Then at year 8, you kind of dabble into the idea of Cartesian planes, and you take this table. So once you work it out, so 0 times 2 gives you 0, 1 times 2 gives you 2, 4, 6, 8. There was a pattern. Then you plot this onto a Cartesian plane, which for some students, that was then tricky at year 8. It was understanding that, when it goes 1, it goes 2, so you get a point. You get 2, it becomes 4. So there was a pattern that it ends up being linear. They don't know that, they just put the dots. And then at year 9, that's when you start doing y equals mx plus c, where we're like, well, instead of doing 5 dots to get a straight line, you then learned that there's only 2 points that you need to sketch a straight line, which is there where you learned how to find the gradient. So y2 minus y1 over x2 minus x1, and then your y-intercept. And then you use your algebra that you learned from year 7, 8, 9 to then solve these problems. Perpendicular, parallel, year 10, yeah? So you see the transition. But where or what graphs do you truly learn up until this point? It really is only linear, and in year 9 and 10, quadratics. By the time you get into year 11 now, we are going to assume, usually, we assume that you are masters. Technically, by the time you start year 11 methods, term 1, day 1, you should have been masters of these 2 points. The reality is that's not the case. Most students do not have their algebra. Most students do not fully understand what a linear equation is. They can't picture it. So they're still working about at the year 9 level. Yeah? And that's where they're non-accelerated. They're essentially doing what you guys are doing at the moment. I'm teaching them linear equations, perpendicular lines, and all that. So your chapter 2 is what they're doing. So it means that at year 9 level, you are able to figure this part out. The quadratic part, they will also learn in term 3, and they'll learn exactly what you guys learn, completing the square. So you learn everything to do with quadratics. So you've got linear, quadratics. Now, what you're going to be learning that is different to the year 9 accelerated, because they won't learn it yet, is that you're learning other functions besides just y equals x to the power of 1. This is y equals x to the power of 2. Next term, you're going to learn y equals x to the power of 3, which is cubics. And all of that requires everything you know beforehand. 7, 8, 9, 10. You need to know all of that to do that. Okay, that's why it builds on. This chapter, though, you're now looking at, well, what if it's not to the power of 1, 2, 3, 4, 5, or 6? What if it was root of x? What if it was 1 on x? And what if it is 1 on x squared, which is, if I had to summarize it for you, that is exercise 4a. This is 4b, and this is 4d. So let's recap. Do you remember, in the same thing, I taught you transformations from chapter 3. You just need to remember the shape and properties of each one. Let's go with 4a. What's this shape or this function called? So we learned linear, quadratics. What is this one? Exercise 4a. What is this one called? Can I please have... That's from our last session.
We don't need a new sheet.
Yeah, new sheet. Unless you don't have it, then this is the last copy. What is this called? Hands up if you know. What is this called? Numafi. Rectangular hyperbole. In specialists, it'll just be hyperboles, because then you look at all variations of it. But rectangular hyperbola. So, what does it look like? Let's recap. Rectangular hyperbole, if you have a y equals 1 on x, one of the first things is you have to look for a problem. What is a condition that you can't have when you have a fraction? What can't you do with a fraction? There's something you can't do. So that x value, there's a number where the fraction would not work out. What's the number? 0. 1 divided by 0. A lot of students think it's 0. It is not. That is undefined. Try typing in your calculator. It will say error. So that means when x, on the x-axis, when x is equal to 0, you won't have an answer. So that means there should be this dotted line, the vertical line. There should be any points at all. So this is your vertical asymptote. That's what they call it, asymptote. We know that when x equals 0, there's not going to be a point. We call it a vertical asymptote at x equals 0. They need to see x equals 0 when you're writing in your asymptote, right? There is also another point to note as well. The question is, can you ever do 1 divided by something to equal 0? Now, in a logical sense, you think about it. If you, in terms of numbers, when you say 1 divided by 2, you get half of it. 1 divided by 3, you get a third of it. 1 divided by 4, you get a quarter of it. So 1 divided by what will give you nothing? Yeah, there's nothing. There is no way that you, if you're able to divide, because numbers goes infinitely, that means you can infinitely divide a number. That is why it's impossible for y to equal to 0. So on one hand, x can't equal 0, but it's also impossible for you to divide 1. You can divide it very close, it gets really small, but it's never exactly 0. So hence, you also have a horizontal asymptote. So anytime you get a fraction, that's one of the properties. That's one of the first things you should think about. So you can't have 1 divided by 0, but if you can do 1 divided by something, it can never actually equal to 0. So hence you get 2 asymptotes, you get a horizontal, you get a vertical, and this is what your shape looks like. Okay, that's a rectangular hyperbole from your notes from before. Let's recap then. Let's look at exercise 4b. What is this one called? Hands up if you know. So 1 on x squared. Truncus. Very good. And that name hopefully will help you remember the shape of the graph. It looks very similar to your rectangular hyperbole because it has the same properties. When you have a fraction, you can't have x equals 0. And you also can't have 1 divided by anything to actually equal to 0. So it has the same asymptotes. The difference is you're squaring. And one of the properties that when you square an x, what's nice is every time you square a number, it is always positive. No matter if it's a negative number or not, it's always going to be positive. So what's the difference between the two graphs is that when I put in a negative 1, I'm not going to get 1 divided by a negative number, which gives you a negative value. That's why the graph goes down. Over here, the graph remains positive. That's why it kind of looks like a tree trunk. Okay, so you can think of it as like a truncus. So a tree trunk, and the reason why is because when x is negative, whether you have negative 1 and you put negative 1 into the function, the y will always equal to a positive value. That's why that y value corresponds to a positive point. Okay, and that's why the graph looks symmetrical. Okay? And then your last one, which arguably to me is the easiest one to sketch compared to the other two because it's fractional. That means you have to be good with your algebra with fractions to solve axis intercepts. But surds, it's actually much easier. Surds. Now, notice that I skipped exercise 4c. There is a difference between 4c and 4d in its name. 4c, for your information, this is called square root relation. Whereas 4d, this is called a square root function. There is a difference between a relation and a function, which you guys haven't learned yet until we get to chapter 5. Then I can briefly tell you what a function and a relation is, what's the difference. But on Desmaster, you can clearly see the difference. I'll show you. This is a square root relation. Y squared equals to x. Can you see how it kind of looks like a parabola, but it's just on the side? So normally we have y equals x squared. What's interesting is if I square root both sides, this will now give me y equals to square root of x. True, by square root both sides. So technically this one should equal to this one. But notice, if I take this one off, I only get half of it. This is what we call a function, which you'll learn in chapter 5. Don't fret over it. You only get half of the actual shape. It's actually meant to look like this. That's the proper shape for it. But that's not a function. That's a relation. And so we are skipping 4C just so that you don't get confused about relations and functions. And then hence we're only focusing on square roots. Because you only get, that's a positive root, so positive sign in front of the square root, that's why you get the top half. If you wanted the bottom half, put a negative in front of it, and together, that plus minus, when you square it, you get a plus minus answer. That's what you're getting here. That's the top half and bottom half. Okay? Whereas the y squared equals x, that's the full entire thing. It's like a parabola on your x-axis. That's a relation which we won't go through as part of our course. Yep.
When you don't sketch the dilation properly,
You'll be fine at year 11 and 12 only because you can't tell. The only way to actually show that you have a dilation is you pick a point. That's why your textbooks, they usually do this. If there is a dilation, say I gave you y equals 2 root x, for example, you find that 2 root x looks very much the same as root x. But if I do it on Desmos, you can see the difference. So root of x is still going to look like that. It starts at 0, doesn't move left, right, up, or down, and it's going to look like that, right? 2 root x looks exactly the same, doesn't move left or right, but there's a 2 in front of it. Now, dilation means a stretch, so it does look slightly different. It should be thinner. So on Desmos, you can see it. So if I delete this, I delete this, I delete this, let's type it in. Y equals root x. This is what the original graph looks like. As soon as I put a 2 in front of it, that's what it looks like. But if you were to draw it, and I gave you this as part of your SAC, I said sketch that, no one knows if that's a 2, that's a 1, or 3, or 7. So how do you do it? If you want to do it properly, and the textbooks do it, but you don't get penalized at year 11 and 12, the textbooks do this. They just say pick a number. If x equals 1, then according to this equation, when x is 1, root of 1 is 1, 1 times 2, y equals 2. That will show you the difference, and that's how you show people that there is a dilation, because if it was root x, it would have been 1, 1, and not 1, 2. Okay, so that's an example of how you would show a dilation. So if you're looking at your textbook and you're wondering why there's a random point, they usually pick 1 because it's the easiest one to do. Okay? But you don't have to. It's just, that's why with dilations, that's why I haven't talked a lot about dilations. I've only talked about left, right, up, and down. And I've only asked you to sketch by looking at up, down, left, and right. Because when you sketch, dilation's harder to see, but the movement, everyone knows where it should be. Okay? So that's a quick revision of the 3 functions that you have seen. Doesn't mean you've learnt it. The worksheet I've given out today, so you should have one of these ones here. That should substitute for your exercises A, B, D. If you found that that was not, or there was too many questions, this is a summarized version, but this is harder, okay? Because I put in some more questions in there that has more negatives and more movements. So this one, if you can do, means you truly get it. If you can't do it, go back to your exercises to reinforce your understanding, okay? Now, there is one graph I haven't shown you. In your notes, notice that I've only covered the first 3. Rectangular hyperbole, truncus, square root function, circle. Now, circle can get tricky just because a lot of students are afraid of square root signs. Yeah. Oh, yeah. Anyone else who hasn't got these worksheets? All right. Here we go. Circles. Can you write the equation for a circle? Cross this one off. Forget about the y. I forgot that you don't start off with y because technically this is not a function. It is a relation. Functions usually start with y equals. So this one, the equation is x squared plus y squared is equal to r squared. Write that in. That is the equation for a circle. Let's read what each one does. R stands for the radius of a circle. X, obviously, anything to do with moving left and right, because it's the horizontal axis. Y is anything to do with up or down, because it's your vertical axis. Today's lesson, you will learn both circles and semicircles. Semicircles are functions, okay? That's why it starts with Y. Circles aren't functions, they're relations. That's why it looks a bit different. I think that students normally find circles easier than semicircles, even though technically semicircles is less work, okay? Because you've got half a circle to work with, right? There's just something nice about x squared plus y squared equals r squared. So I'll show you some examples. And Ben, can we please stop that? Thank you. All right, here we go. Let's do an example. If I said to you, so write this in as an example. If I said x squared plus bracket y minus 1 squared is equal to 4. So write that example down. You know this is a circle because it follows x squared plus y something squared and it equals to a number. This is a circle where the radius, remember r squared has to equal to 4. So what would the radius have to be? If I square the radius and it has to equal to 4, what would the radius be? 2. So this tells me that when you draw your circle, okay, and your normal circle starts with the center at 0, 0, so the center is at the origin, that means the radius of this circle has to be 2, this has to be 2, this has to be 2, this has to be 2. So that means your endpoints are all 2, -2, 2, and 2. Let's see if that's true for now. Okay, I'm going to go to Desmos. Here we go, let's visualize it. I type it in, x squared plus y squared equals 4. And let's zoom in a bit. Can you see how that circle has a nice radius of 1, 2, 1, 2, 1, 2, 1, 2. Okay, so that's x squared plus y squared equals 4. Now the question is, what have I changed? When I got you to copy the example down, I said, let's make it y minus 1. You tell me what's happened here. I'm going to give you the center again. So the center was at 0, 0. Okay, that's where the center is in green. I'm going to label it. Let's see what happens when I do this. Put a bracket in and I say y minus 1. Let's zoom out a bit. What happened? Moved up by 1. The center now is 0, 0, 1. Can you see that? The center is now at 0, 1. So 2 across, 2 up, 1, 2. Now that's at 3 maximum. 2 down, 1, 2. Now it's at -1. Across, that is 2, 1, -2, 1. So usually what you've been used to is that anything that you add on the outside moves up or down, right? But because the y is exactly here and you're affecting y directly, this works the way how I've taught you with x's. Whatever you do to the x, I say let that equal to 0 and solve it. That's what you do for the y's. So in this scenario, if you want to know if it moves up or down, this is what you do. I'm going to highlight it. Whoops. Highlight it. Let this equal to 0. So y minus 1, let it equal to 0. And if you solve for a y, what should y equal to? 1. And if it's positive, it will go up. If it's negative, it will go down. Okay, so in this case, this is y is equal to 1. So that's why we know it is up 1. Okay, so this is only slightly different to what we've been doing, but it's the reason why is because the equation is different too. Okay, let's try another one. I'm going to go to the exercise itself. Let's see if you can pick up on reading it now. So let's go to exercise 4E, circles. Where is it? 4E is just over here. Let's see if you can read the circles. All right, let's pick this one over here. It's not a nice number, actually. Actually, we'll do this one. All right, let's just look at this one. How do you know this is a circle? Again, you've got x with something squared and then plus y something squared. That should be a big hint to you. It is going to be a circle. Problem is, I don't have r on this side. How do I get my r? Good. Add 169 on both sides. And so this is your new equation now. You're going to get x plus 1 squared plus y minus 4 squared is equal to 169. But let's read that. What's my radius? What should the radius be? 13. Square root it. Okay, so something times itself will give you 169 because remember it has to be r squared. So clearly 13 squared will give you 169. That means radius is 13. Let's read. This should tell you left or right, and this should tell you up or down. Using some quick maths, Ben, am I moving left or right? Left by? Good. This is left by 1. How do we know? Let x plus 1 equal to 0. Solve for x. X equals -1, so it tells you left by 1. Next one, Lockie. This should tell me up or down. Up by 4. Very good. Again, same thing. Let y minus 4 equal to 0. Solve for y. And y is positive 4, so it tells me up 4. If I ask you to sketch this circle now then, you know the radius is 13. First, find the center. So here we go. Draw an axis. You told me up by 4, so 1, 2, 3, 4. Up by 4. You told me left by 1, so left by 1. Here's my new center. So if the center's there, remember, the radius is 13, so I got to go 13 this way, 13 that way, 13 up, and 13 down. Now, if you think about it, from -1, if I add 13, that should give me a maximum width of 12. If I subtracted 13 this way, then I should have -14. That's the between -14 and 12. That's how big my circle should be. Vertically, though, I started off at 4. So from 4, I'm going down 13, and from 4, I'm going up 14. What I should expect is 4 plus 13 should give me 17, so maximum value of 17, and 4 take away 13 should give me, what's that, -9? So my circle, when you draw it, which I'm doing a very terrible one at the moment, you just need to mark center, 17 on your axis to show that that's the highest point, -9 is your lowest point, 12 and -14, and that's how you would show that you've got your widths. Yeah. No, just on the axis. You don't actually need to label the coordinates, the widths. You need the center though. The center must always have a coordinate. So our center should be labeled with -1, 4. So let's see on decimals. Let's see if this is true. I'm going to delete this. Let's have a look. X plus 1 squared plus y minus 4 squared is equal to 169. I want to zoom out. And let's have a look. So the width, can you see how that's -14? They don't put a point here, but they say -14 is the largest width that you can have. Oh, so smallest width you can have. And then if I go to, sorry, I just changed the, there we go. And then if I look at the bottom, -9 is the smallest on the bottom, largest on the top, 17, like we said, and then all the way to the right, maximum of 12. Where's the center? We said the center should be at -1, 4, and that is the center. So it should be 13 across, 13 up, 13 down. Make sense? Okay, so it's very similar to what you've learned so far, up, down, left, right. Don't worry about dilation circles because it's a perfect circle. Your job is to draw it with the correct maximum, minimum axes for both your domain and range. Okay? Yes, it can. Okay, that's a good question. So on your CAS, on your graph, you see when I press tab, notice it's F. The reason why is because it's in function mode. That is not a function. That is a relation. So what you would have to change, because you can't just type x squared plus y squared since you already got a y there already. So you have to actually change this to not a function mode, you have to go to menu and graph entry. Okay, so menu number 3, can you see how I'm always starting in function mode? It's a relation, or you can use templates. So they have some templates there, but because we've got a relation, if you go to number 2, now it doesn't have the f at the start. So you can actually now type x squared plus y squared is equal to 169. And I need to fix my graph actually. Menu for 1, oh, sorry, menu for A, menu for 5, standard. And maybe I'll change this to 4 just to make it easier. There you go. Can you see that circle? Now you can sketch a circle. And the reason why I still have the cubics is from the last time we were doing it. That's your function. So you will have to switch between function and relation if you want to type in what it is. So I got to go back to 4, graph entry, 1, delete this, and then now you can just see the relation. Okay, so if I go back to menu, 3, relation, I can now edit my circle. Here's my circle, make it 9, and I make the circle a bit bigger. Make sense? There we go. So you can sketch a circle in your CAS, you just have to change the graph entry. Can't be a function, it has to be a relation. All right? All right, team. One last one now. So you learnt a bit about circles. Back to your notes again. Just underneath your notes, I gave you the formula for semicircles. You can memorize this, or you can solve it yourself. Where'd this come from? This plus or minus? This is where it comes from. You had your x squared plus y squared is equal to r squared. If you just rearrange it, that's all it is. So if I just move the x squares across, you get y squared is equal to r squared minus x squared. What's going on? It's so laggy. R squared minus x squared. Square root both sides. But remember, when you square root, what should you have? Plus minus. Why do you have a plus minus in a function? I'll show you what it looks like. Let's say I gave you x squared plus y squared equals 4. That means a radius of 2 for the circle. Well, then your equation would be plus minus root of 4 take away x squared. That's what it'll look like. Okay? Let's see what it looks like on Desmos. I'll go back to Desmos and I'll just take this off. If I type in y equals the square root of 4 minus x squared, can you see how you get just the top half of the circle? Because that's the positive root. If I then said y equals negative root of 4 minus x squared, you get the bottom half. So that negative is a reflection. That's what it does. But notice in your notes, I also got a second formula for you. What if you didn't rearrange for y, but you rearrange for x? What happens then? Let's see what this looks like. What if I changed it and I said it was x equals to square root of 4 minus, what do you think it's going to look like? Very good. It's a semicircle, but on the left and right. Oh, sorry, that should be y. There we go. Can you see that? The positive root will give you the positive side of the x-axis. First half, so it's a semicircle, but it's a vertical one. And if I did the same thing with a negative, you get 4 minus y squared. You get the other half. Okay, so everything is still the same. If I want to move this graph up or down, it's the same thing as what you've been doing with square roots. If I put a plus 1, if I put a plus 1 here, it will just shift it up. Oh, sorry. Because it's x, it moves across by 1. Sorry, my bad. Let me go back to this one. It's easier to understand. If I put a plus 1 here, it shifts the graph up by 1. If I said minus 1, it shifts it down by 1. Okay, so everything's still the same. If I want to move it left or right, change the x. So x minus 1, for example, we'll move it to the right. Can you see that? Everything's still the same. Whatever you do to the x, and what do you add on, will then move up or down. Make sense? Oh, okay. Sorry, team. Can you guys listen to this bit here that is important algebraically? Listen to this bit. Oh, sorry. What's going on? All right. I think there's too much inking that it can't handle the mathematics going on right now. Anthony asked this question. You got 4 minus, let's say if I said x minus 1 squared. So this is a semicircle that moves to the right by 1. I can tell it moves to the right by 1 because I'm looking at that one. Radius of 2. Now, he asks, can you just square root the 4 and then keep that square root like this? You can't do that because remember in surds, if you had root of 5 plus 2, you cannot, that is not the same as saying root of 5 plus root of 2. What you're confusing that with is root of 5 times root of 2. Yes, that is the same as writing root of 5 times 2. Okay, only times that you times inside, if it's add or subtract, you cannot separate them. So this one, you can't separate it and say, oh yeah, I've got a positive 2 on the outside and then it's a plus root inside because you're not following the surd rules. Okay, so the surd rules are adding and subtracting. It has to be the same surd. So root 5 plus root 5, you can add those together and say it's 2 of these root 5s. What you don't do is you don't say that's equal to root 10. It's not the same thing. Okay, so if that's confusing to you, that means there's some surd algebra from year 9 and 10 that you need to brush up on. Okay, we don't go through that in year 11 methods, but I will pick it up as I'm looking at your homework and your layout, whether that's going to be a common issue you need to work on. Okay, so only when you times that you can separate them. So for example, if it was 4 root of 4x minus 4 squared, yes, this scenario, you can do what Anthony was saying. You can actually split that up and write root of 4 times root of x minus 4 squared. That's fine. Okay, then that would have been 2. And actually, conveniently, this cancels out as well. So we're in 2x minus 4. Okay. Anyways, that was a bit of algebra. Just to clarify, you can't split the surds if it's plus or minus. You can split it if it's times or divide. Okay? All right, team. That's a lot of information about circles, especially if you haven't practiced rectangular hyperboles, truncus, and square roots. I want you to either have a look at your exercise or this worksheet. This worksheet is going to be testing you. If you want to start easier, flip inside. The one that says 4ABDE homework, that one starts off easier. Okay, so I start asking about asymptote, then I ask about solving using algebra, and then on the back of the page, you then do a bit of sketching. Okay? So then you do a bit of sketching on these slides. So I think the inside might be easier to start off with. For those who are confident, you can start off with the first page. It's summarizing everything that you've meant to know. Alright, I'll come around and help. There are a few students I do want to speak after class. I'll call you out later. And then just see how you're doing.